Okay, so on Wednesday, we left off right at Tempur-Martensite embrittlement, or irreversible embrittlement, and then we had just finished off by talking about Tempur embrittlement, which is sometimes called reversible embrittlement or steel sickness. And this was called reversible because, well, Tempur-Martensite embrittlement was considered irreversible because once you dissolve the grain boundary cementite off at a higher temperature, cooling back down, you won't grow a new grain boundary cementite layer. Tempur embrittlement, as I muddled my way through on Friday because I was looking for the word salad that is this slide, occurs by a very different mechanism. And so it's reversible in the sense that if you heat above this range of 450 to 600 C and then cool back down, you'll get the embrittlement. And hold in this regime, you'll get the embrittlement back. So basically, highlight on your, wow, this slide is so confusing. I went through it and I had a specific thing I wanted everyone to highlight. Okay, so this last bullet point here, right? So you have the co-segregation of elements antimony, phosphorus, arsenic, and tin, right? And they are going to co-segregate to the grain boundary and reduce the cohesion energy, right? So everyone highlight this last bullet point, right? This is the main idea and the main important. And as I said, for next year, I'm going to simplify this slide quite a bit. Okay, so the other thing to know is that molybdenum and titanium and zirconium are present. Essentially, you get a scavenging effect, right? They essentially have the same attraction to each other, but it's much stronger, and they don't precipitate at the grain boundaries, right? So the idea is we need to keep these impurities as low as possible, right? And this becomes an issue with waste stream recycling, right? A lot of depending on, we'd say a lot of the steel manufacturing in the U.S., right, is essentially arc remelting, right, for specialty grades, right? Because we don't make a lot of commodity steels here anymore. It's much cheaper to produce those steels in China and India, right? The basic carbon steels that we use for building. But for higher grades of steels that we produce a lot in the U.S., we do a lot of arc remelting from scrap, right, mixed with amounts of virgin steel and recycling. And we have to keep a very close eye on the impurities, particularly these guys, for this exact process. Right? Yeah.
What's something that reduces the energy of grain boundary, reduce the cohesion?
Right. It just means you have to put less energy in it to split it. Right. Right. It's the same as a continuous film of a cementite. Right. Well, in that case, it's cracking of the cementite, but in general, whenever you have something that's going to wet your interface, right, and have low energy, it's also going to be a very easy fracture path. the example at the beginning, I think I gave bismuth and copper, right, were well less than 0.1% will completely coat. Yeah.
The last point of
The last point of the second one.
the larger amount of
Right. Titanium, zirconium are exceptionally strong carbide formers, right? And so I don't have a source for this, and this is one of the reasons why I want to produce a new slide of this for next year, is the argument here is that if these are present in too high of a concentration, the carbon, right, and I don't understand the rationale for this, making the argument that carbon will react, releasing these impurities back, right? Right? If, or I guess you can think of it this way, you're going to have impurities and molybdenum tied up, right? If you have a more molybdenum than you need to tie up the impurities, it's still not going to, right? Right. I'm not sure about this point in this example, right? Why having more molybdenum there? All right. So this is the danger, right? I'm using these slides because 95% of them are so good, but every so often I'm finding things like this that makes me question details, right? And this is much more than I want or expect anyone to know about this, right? The main idea is for the purposes of this class, knowing that this TME and temper embrittlement exist, right? And that it's really grain boundary phenomena that leads to the embrittlement is really the important thing, right? The details of it are not so critical, right? And so next year, essentially, I'm going to replace this with like a couple bullet points on the slide. But this, you're right. This bugs me because I'm not sure. I started thinking about it. So you have an overabundance of molybdenum, more than you need to tie up with the, right? If the affinity for carbon is more to form a carbide, you could split these off. The impurity atoms can segregate to the boundaries by themselves, but yeah, but you would need significant amounts of nickel in there as well, right? So if you can imagine if the affinity is higher, then it's not going to matter if you have an overabundance or not. It's still going to split them up. Right? This is where this is the thing that confuses me about this statement. Right, is anyone else following the argument I'm making here? Right? What it seems to be, what this slide seems to be saying is too much molybdenum or zirconium, or titanium, very, very strong carbide formers. They're going to suck up all these impurities, but then slowly over time, they're going to form molybdenum carbides or zirconium carbides, releasing the impurities to go to the grain boundaries with nickel and manganese and form this, right? That would slow it down, but it should happen at a rate that's irrespective of the amount of molybdenum that you have over, right? It should happen whether you have the exact right amount, slightly less, or way too much.
And you actually can, like carbon can replace the impurity of them. And diffused carbon is anyway going to be first, right?
Yeah.
The first carbon will get in there, so the segregation will not have enough time to get in there.
Yeah.
So if it's gonna form carbides, or form carbide in the first place.
Yeah, it's going to form carbides anyway, right? So I'm not sure about this statement, and there's nothing in like I didn't see anything in Badish's steel book about how an excess of molybdenum, right? So sometimes I was kind of hoping that no one would ask that question. I figured Kamal, he has a knack of asking the question that I don't want asked, right? But yeah, that kind of bugs me as well. Okay, well anyway, whenever we're heat treating, you have to worry about cracking, distortion, warping, right? And these really come up when we have large changes of cross-sectional area, right? Where you have differential cooling rates through your sample. That's going to potentially cause these problems. So that's kind of some bulk treatments. Surface treatments, this is all really for awareness, just so that when you hear the term, you're aware of what they are. There's a lot more details here than we ever need to worry about, right? And so these are essentially plain hardening mechanisms or thermochemical treatments, right? They both lead to, for the most part, often lead to localized hardening at the surface. This tends to have to do more with carbon, and this with other elements, right, being the primary. Well, so in for flame hardening, essentially yes, right? This is the simplest form. You're just heating up the surface locally. You're not heating the entire cross section of the part, right? And then spray quenching, right? Then tempering the parts very slightly to relieve the residual stresses, but not diffuse too much carbon, not deform too much carbon out, right? And you'll see this term case depth, right? You've heard case hardened tools or case hardened steel. That's the depth of the surface layer that's been hardened, right? So what's one benefit of hardening just the surface over the whole workpiece? It's all about, right, strength and ductility balance, right? If you think about a chisel blade, right, you want a hard edge at the very tip, but you don't want the whole shank to be hardened, because otherwise you're going to break your chisel, right? You can chip the end and resharpen it, but if you fracture the whole shaft, you're done for, right? The tool's useless. And so basically what this is, giving a very strong, hard surface at the top, and then a soft core which can absorb energy. Induction hardening is the same thing, except now you're going to do use an induction coil for the heating, right? And an induction heating, especially for short periods of time, is not uniform through the depth, right? The depth right, the magnetic, right, your field interactions tend to happen more at the surface than in the center, right? But the depth that you're going to heat is going to be dependent on the frequency and the strength of the field, of the alternate in the field in your that you're using, right? So essentially, it's the same thing as flame heating, except instead of using flame, you're using
But heat will be generated even in the center.
heat is generated in the center, but it's not uniform. It's not linear through the thickness, right?
So even the center will be heated.
The center will be heated, right? So you have to. It has to be designed very carefully for what the.
Heating, so your induction coil actually induces currents in your sample due to the skin effect. So your currents are actually higher concentration on the outside of your sample.
Yeah.
And so that's what's causing the heating. Your magnetic field decreases substantially with distance. It's R squared. So it's largely the outside of the sample. It's also frequency dependent.
Yeah, and it's also very short times, right? So you don't have to worry too much about transport, right? Okay. So then, essentially, right, laser hardening, right? You're just giving it a very high, very focused laser pulse, right? So you're doing both heating, but you're also putting in compressive stresses at the surface, right? This is also has a peening effect as well as just a heating effect, right? So you have very thin surface zones that are heated and cooled, so you get very fine martensite near the surface. But if your shock laser power is high enough, you also get a shock pulse that goes through and gives you compressive stresses on the surface for a much thicker depth than the fine martensite, right? So you have resistance to crack opening at the surface, as well, right? Since the depth of heating from the laser is very small compared to that for induction or flame hardening, you have a much thinner case hardened layer on the outside. But again, you have that compressive stresses that you get from a peening operation as well. Right, so essentially electron beam is very similar, except instead of a laser to do the treatment, the heating, you're using an electron beam, right? So the benefits are you can do complicated cross sections that you can't do by induction or flame hardening by electron beam. What's the big downside that's not really mentioned here on this slide? You need vacuum, right, to control the electron beam, right? So your parts need to be under high vac, right? So it adds a significant amount of complications to the process, right? Okay, so carburizing, right? This used to be something every welder was really, really good at, right? Because essentially what you're doing with carburizing is putting it into an environment where you're enriching the surface layer with carbon and making it tougher, right? So often carburizing is mixed up with flame induction or flame hardening. because the simplest way to do this, or one of the simplest ways to do this, is if you take a oxyacetylene welding torch and you make it a rich mixture, your torch is going to burn cooler and have an excess of carbon, right? Mostly in the form of carbon monoxide, which is going to react with iron at the surface to give you interstitial carbon in your iron and the 2 carbon monoxide to CO2, right? So you've got carbon dissolved in austenite, right? And so then you have a quench will produce more martensite at the surface. Or even if it's slow cooled, you still have a locally carbon-rich surface, right? So that's the easy way to do it with a welding torch, but you can also do it in batches, either in pack carburizing liquids. You can put it in a carbon monoxide environment, right? And so then you would want to, there's a whole range of post-carburizing heat treatment, right? And one of the key things is a balance between a high hardness of the surface and improve the microstructure at the surface, and then break the carbide network, right? So this is, if you, due to the higher carbon content, right, you might have, depending on what your alloying elements are, you can have clusters, right, or flocculation of the carbides in your sample, right? And essentially, these are very short time treatments, right? So you're going to go up to above 1,000 C with an oil quench, right? A temper to convert any retained austenite into bainite, right? Then a very rapid austenizing temperature back up, an oil quench, and then a final temper, right? And so one of the questions to ponder is thinking about how on earth this actually achieves the aims that are put out there. Okay. Other chemical processes that are common are the cyaniding and carbonitriding, right? The main idea, again, is these are chemical processes to get more interstitials in, cyaniding carbon and carbonitriding nitrogen, right? So these are basically done in a molten salt bath, right? And again, the process itself is not important. It's just knowing that they exist. So when you see the term, you know what it means. I guarantee you're not going to see questions about cyaniding. Right. Right. Same thing with nitriding, right? You're just dissolving interstitial nitrogen into the steel. Right. Same thing. Boronizing is often done in plain, well, not often. It's kind of a rare thing, kind of newer, but plain carbon steels and tool steels, right? You're going to put it in a box containing a bunch of boron carbide, which when heated up the gas is going to diffuse into your sample. You're going to form iron boride and diboride, right? And basically this is just additional precipitation, hardening at the surface. Chromizing, right? Same kind of idea, right? Okay, so the last parts of this, and then we're going to get out a little early today. So we've got two important things to discuss that can form a beautiful basis for a wide range of jumping off points for exam questions, right? So this is something that you should at least think about, right? And this aspect of controlled rolling or finished processing, right? So in steels, we want very high strengths. So we're going to heat above the upper critical temperature, right? Giving us a stable austenite, right? And then we're going to deform, right? Why are we going to deform at high temperatures? Because we want to recrystallize in the austenite phase so that we have a very fine austenitic structure, right? So if we just take up high temperature and sit, we're going to grow the austenite grain size out. Right? But if we deform in the hot condition in the austenite regime, we can recrystallize, have fine grains, right? Where we're going to check the grain growth by both the deformation processes and, importantly, by the presence of second phase particles. So we have to know what our alloying elements are and making sure we're below the solvus for any secondary phase reinforcing particles of interest, right? So super important are the strong carbide formers: niobium, vanadium, titanium, zirconium, right? Yeah.
So upper critical temperature is H3.
Yeah. Yeah. All right. All right. So the idea: fine austenite grains, fine ferrite grains, because in almost everything that we talked about, ferrite grains nucleate at prior austenite grain boundaries, right? Okay. So that's basically the gist of why we want to do this. So what is the what's sort of, I guess, the design problem that led to the development of this kind of heat treatment, right? It's expensive to do hot working, right? So we don't want to do it unless we don't have to, right? So if we think about what's in plain carbon steels, we've got carbon and manganese for strengthening, right? So too much carbon, though, gives us a embrittlement problem, toughness problem, right? We have too much perlite. So this is really the motivation for a fine grain size. We want to keep the cementite regions, right? We don't want these large single perlite colonies, right? Okay. So the schematic of this is is pretty simple, right? Now we have it's kind of the flow chart of different controlled rolling operations, right? If we fully recrystallize, we have equiaxed austenite. We don't fully recrystallize, we have pancaked austenite, right? And we'll talk about why we would want one or the other in a little bit. But we need secondary phase particles to pin the boundaries, right? So that we can slow the grain growth. Slow the grain growth down. So we're going to add our grain refining elements, carbide and nitride formers, niobium, vanadium, titanium, and aluminum. Right? Okay. Right. And then this is basically just showing the final grain diameter as a function of the finish rolling temperature. So during this dynamic recrystallization during the rolling process, what is the final grain size going to depend on? Right? If we were in the absence of any grain refiners, right? Right? We'll leave the pinning out of the discussion for a second. In the absence of strong carbide formers that are going to act as grain refiners, what is the final grain size going to depend on? The what? Temperature and strain rate. Right? So if we have grains that are smaller than our steady state grain size for those temperatures, right, our grains are going to essentially grow during the recrystallization process. If our grains are bigger, they're going to be refined, right? So essentially, those are the knobs we have to control, right? We need it to be hot enough that we're going to have recrystallization, right? We need it to be cool enough that we're not going to grow too much, or we have to have enough grain refiners in there to provide pinning and keep our grain size small, right? Okay. Going back to the flow chart, we have two options, right? If we stop recrystallizing, if we stop rolling when we're in the high temperature regime, right, while we're still in the austenitic regime, we're going to have a fully recrystallized equiaxed austenite structure. If we keep rolling as we cool down, right, we're going to reach a point where we're not really dynamically recrystallizing anymore. We're going to have pancaked austenite grains, and this can lead to a very fine final ferrite structure, right? Because we have a huge amount of grain boundary area to serve as nucleation sites here. So one of the common practices is to keep rolling as we go down through the austenite to ferrite transition and into the fully ferritic region to get very fine final grain sizes, right? So of course, there's nothing new here, right? This is essentially Hall-Petch effects and dispersion strengthening of the secondary phase carbides, which are also our pinning grain boundary refining elements. Right. Okay, and so if we look at the effect of the different, where the our strengthening comes from in high strength, low alloy steels, right? So these will be with small amounts of other alloying elements, right? We can see the effect of different aspects, right? This is as a function of manganese concentration, right? But basically we see, here's the solid solution strengthening, right? Nitrogen and silicon are the other alloying elements. The effect of solid solution strengthening of manganese, the grain size reduction, right? You see that as we increase the manganese, we are able to get a final smaller grain size. Precipitation strengthening is pretty parallel because the manganese doesn't enter into the precipitation reactions. This is the niobium carbide, right? So this is the effect of having a strong carbide former in there. All right, so we get a benefit from having a much finer, right? The benefit of the controlled rolling with carbide formers to refine the grain size is twofold, because we also get a small grain size, but then we also have a boost from the precipitation strengthening after the transformation. So dual phase steels, we're going to talk more about in the advanced high strength steels next, right? But basically the idea here is we have ferrite and martensite mixed, right? So we have good strength and strong reinforcing, right? This is really more of a composite than a single, than what we would typically think about, because these martensite particles are very hard, very tough. They act much more like a ceramic reinforcement than a different phase of steel in this case, and then very soft, soft ferrite, right? And we'll talk more about this, but I want to I threw this slide in here because I want you to start to think about what processing route you would need to develop a microstructure that's like this, right? How do you have the stable martensite surrounded by ferrite, right? What is the process you have to go through? And we'll talk about this, but think about it and reflect on it for a little bit, right? How on earth can you do this? And this is a relatively new idea in steelmaking, right? So it might not be immediately obvious, right, how this kind of comes about. It's not a quiz or anything, right? It's just, right, get your brain thinking. Okay. So HTMT we deformed way up here in the austenite regime, hot cold working. Right. So HTMT is essentially what we just talked about, right? We're deforming high in the austenite phase field. This aus forming, right? It's just this is just another abbreviation. Right. Aus forming, on the other hand, we're going to quench down fast enough that we miss the nose of the pearlite and bainite bays. We're in this regime of metastable austenite between the two phases. We're going to deform, right? If we were lower down, we would catch the nose of the bainite. If we were higher up, we'd catch the nose of perlite, right? But we can get this, if their composition's right and we have a sufficient gap here, we can deform in this intermediate, but we're still completely in the austenite phase field, right? But it's super cooled austenite, right? This is very heavily deformed, right? It's not going to recrystallize. We're not hot enough for that, right? We don't have significant grain growth that's going on, right? And so we quench down, and we have, we're fully martensitic. But what's the point of doing this forming process here? I realize it might be kind of silly to ask this question when the notes are up here and everyone has it. Right, but we're put in a whole bunch of dislocations, right? What likes to nucleate at dislocations heterogeneously? Right? Are secondary phase particles, right? So this LTMT, or os-forming process, is vital to getting really high degrees of secondary hardening, secondary strengthening out of steels with strong carbide formers, right? Because we can nucleate all these, a very fine dispersion of carbides at the grain boundaries, right? Okay, so right, that's basically the main ideas that I wanted to throw out there. Right, carbides associated with dislocation. There's a minor, we can ignore this about stacking fault energies. It's a minor thing, but basically, depending on the alloying elements, you can adjust the stacking fault energy, and then if you have a higher stacking fault energy, you're going to have a lower work hardening rate, so you're going to get a lower strengthening effect out of os forming. Right, so it's a minor thing, but you have to keep in mind what other alloying elements are in there. Right, it's not a isolated sort of system. Right, and that's really the end of this heat treatment stuff.